Here are our topics covered today. We will begin by asking the question, what exactly are wing platforms, followed by looking at rectangular wings, elliptical wings, tapered wings, and swept-back wings. Finally ending it off with explaining glide ratio and the sink rate. So, what exactly are wing platforms? Wing platforms are simply the shape and layout of the fuselage and wing of a fixed-wing aircraft. Basically, it's the top-down view of an airplane wing. Now, there is a nearly endless variety of wing platform designs that were developed and improved upon in the history of aviation for both experimental and production aircrafts. Each have their own purpose for use with different aircrafts. So, one may ask the question, why use different wing platforms? Why not just use one wing platform that is the best for everything? Well, the answer is that there is no best platform. Each platform is unique in that it gives its own advantages and can meet different aerodynamic requirements. This can be stealth, control, speed, and more. Let's begin with the rectangular wing. As straightforward as any wing can be, it is a non-tapered wing, meaning that the edges do not angle inwards. It is also a straight wing, which extends out of an airplane's fuselage at right angles. The advantages of a rectangular wing are pretty plentiful. It's one of the easiest and cheapest to manufacture due to the lack of complex curves, and are easy to maintain for the exact same reason. They produce relatively higher amounts of lift at low speeds and have great strength. It also gives strong maneuvering abilities. Now, you may be confused about what this last one means. Desirable stall characteristics? What's that? See, rectangular wings stall from the root. This means that when an airplane is about to stall, the roots are affected first. Root stalls are desirable as it's less severe, so there's relatively less danger. As it warns the pilot for the impending stall, root stalls give ample time for a pilot to recover from the stall. Stalling reaches the ailerons and flaps last, and so a pilot can still control the ailerons and flaps to control the angle of attack even after the roots are starting to stall. This gives a lot of control for the pilot. Now, these advantages may seem pretty amazing, so why not just use rectangular wings all the time? The problem is that rectangular wings also come with some very severe disadvantages, chief amongst which is that they are not aerodynamically efficient at all. In particular, it creates a lot of induced drag. Coupled with this is that it's a low-speed wing, and shouldn't be used if speed is desired. As such, rectangular wings are used mostly for smaller and slower aircrafts, such as the famous Piper PA-38, and also for planes used in agricultural purposes. Next up, we have the elliptical wing. Elliptical wings are wings whose leading and trailing edges resemble that of an ellipse. The advantages of an elliptical wing are weight and speed. It was designed with the idea of reducing induced drag as much as possible. It is a very light wing, and it has the lowest possible induced drag out of all platforms due to the tip being very small. However, elliptical wings have great disadvantages that greatly limit their usability. First of which is that they are very difficult to manufacture due to its compound curves. It is also less rigid compared to other planes and doesn't have much strength. Worst of all, it has undesirable stall characteristics. To explain this undesirable stall characteristics, however, we must first look at lift distribution. Lift distribution simply refers to which parts of the wing produces the most lift. Here we have two different lift distribution curves on a very simplified graph. The blue line is for rectangular wings, while the orange line is for elliptical wings. As you can see, for a rectangular wing, the lift steadily decreases as you reach the tip. This means that most of the lift actually comes from the root of the wing, hence why it stalls first at the root. For an elliptical wing, however, lift is pretty uniform throughout the entire wing. As a result, unlike rectangular wings, elliptical wings stall at the same time, with little to no warning. This is due to the fact that the uniform lift distribution just now means lift is produced pretty uniformly across the wing. If stalling occurs, the entire wing stalls at once since the entire wing is generating lift, and this can quickly lead to a crash. Elliptical wings weren't used very much at all. The most famous use of it was probably the Supermarine Spitfire used by the British in World War II, which ruled the skies for a while. Next, we have the tapered wing. It is a straight-edged platform that narrows towards the tip, hence its name, tapered wing. Tapered wings are a great middle ground between elliptical wings and rectangular wings. It has lower induced drag as compared to rectangular wings, while having better manufacturability compared to elliptical wings. However, this also means that it is a jack of all trades, master of none. It isn't as efficient as the elliptical wing, nor as easy to build as the rectangular wing. In addition, it also has less control compared to the rectangular wing. It also suffers the same problem in regards to stall characteristics with the elliptical wing. Similar to elliptical wings, a tapered wing's undesirable stall characteristics arise from its uniform lift distribution. As a wing is more tapered, the lift is more uniformly distributed, shown in this very simplified graph here. As a result, as a wing becomes more tapered, the wing stalls more and more on its entire surface at the same time. The reason for this is the same as for elliptical wings. Uniform lift distribution means that stalling occurs uniformly throughout the wing at the same time. This means that less warning before a stall and can be very dangerous. Tapered wings were famously used for P-51 Mustangs in World War II, which were used and produced by the Allies to compete with the German Luftwaffe. Last but certainly not least, we have the swept back wing. As the name implies, it is a wing whose leading edges are swept back. Aside from looking pretty cool, the swept back wing has just one advantage, and that is its reduced drag in transonic flights. That's it. One may ask why you would even want this wing if that is the only advantage, but it turns out that this small characteristic is very helpful. Let's check it out. First, however, we need to explain the problem with transonic flight. For that, we must turn to the unit called a Mach. Mach 1 is simply the speed of sound. Mach 2 means twice the speed of sound. Mach 3 means thrice, and so forth. When an airplane moves very quickly, the relative airflow going past the wing is bound to start approaching the speed of sound. This is especially the case at the top part of the wing at the front, where the air, as we said before, gets compressed and accelerates due to the shape of the airfoil. We now bring in a second term, the critical Mach number, which is the speed of the aircraft at which air flowing over the wing reaches Mach 1 at some point. Now, reaching the speed of sound isn't a problem in and of itself. It's what happens when the air goes from above Mach 1 to below Mach 1. When the air inevitably slows down, the point at which the air goes below Mach 1 forms a shock wave, which creates wave drag. Let's say this scenario happens, and a shock wave has formed on this spot. What happens now? Well, the air past the shock wave are greatly disrupted, tripping the airflow and making it turbulent. The air also separates from the wing, resulting in tons of drag and less lift. So, how does swept back wings prevent this? Well, it simply reduces the acceleration of airflow. Due to the angle of the wing, the relative airflow is split into two parts, chordwise and spanwise. Spanwise is simply wind that goes along the edge of the wing, while chordwise is perpendicular to that, like the vertical and horizontal components of any force vector. Now, only wind that flows parallel to the chord is accelerated. This is important as a swept-back wing reduces the amount of wind that flows parallel to the chord, thus increasing your Mach number and delaying wave drag. The only disadvantage of this is that swept-back wings, like elliptical and tapered wings, have undesirable stall characteristics. Let's see this in more detail. Unlike any of the other wings before, as a wing becomes more and more swept back, more lift is produced at the tips, as shown in this very simplified graph, while lift produced at the root decreases at the same time. As a result, swept-back wings have undesirable stall characteristics. Stalling starts from the tip of the airplane because it creates the most lift, and so aileron control is cut off first during a stall. This can cause an airplane to rapidly roll and rock unpredictably and has less warning than if the stall happened at the root. Most high-speed commercial airplanes have this type of wing. If you've flown in an airplane before, there's a great chance that all of your commercial airplanes that you've flown in have used swept-back wings. This is because without swept-back wings, airplanes would have a low critical Mach number and max speed is greatly reduced. Next time, you are able to fly and travel at 500 miles per hour. Thank the engineers and designers of the swept-back wing. Now we move on to some new terms. Glide ratio is simply the distance of forward travel divided by the altitude lost. A high glide ratio means that you move a long distance when your altitude changes, while a small ratio means you move just a small distance. When all four forces of flight are in balance, the glide ratio is constant. Wing velocity has a powerful effect over glide ratio. Tailwind allows your airplane to move faster, greatly increasing glide ratio. Meanwhile, headwind greatly decreases your glide ratio because it decreases your speed. On the other hand, sink rate is the change of altitude over time. A high sink rate means your altitude is changing very quickly, while a low one means your altitude is changing slowly. You can also get glide ratio by dividing airspeed by the sink rate. This is interesting as you can figure out the minimum and most efficient flying speed given information about the sink rate, which is marked with orange here. This is a glide polar graph, which shows the relationship between the sink rate and the airspeed. Now, here at the leftmost part of the curve is the minimum flying speed. Any lower than this and you'll stall because you're not generating enough lift with your low speed. Here is the point of lowest sink rate. Flying at this speed would give you the most horizontal distance for a given amount of altitude change. Here is the interesting point, the point of best lift and drag. Because a higher speed gives you more drag but also more lift, this is the speed at which you will get the best or highest ratio of lift to drag. You can find this point through drawing a tangent line that crosses the origin. So, here's a recap page of what we learned today. Wing platforms are the shape and layout of a wing. Rectangular wings create significant amounts of induced drag but have good stalling characteristics. Elliptical wings create the least induced drag but have undesirable stall characteristics and are hard to manufacture. Tapered wings provide a good balance between rectangular and elliptical wings. Swept-back wings are used for transonic flights to delay wave drag. Glide ratio is the ratio between your horizontal distance traveled and your change in altitude, while sink rate is your change in altitude over time.